Okay, so I want to just begin with a couple of announcements. How many of you are going out of town this weekend? All right, have time to study and do homework, or am I putting it in your travel plans? Anyway, in the interest of the long holiday and students who might be out of town or might be doing a few other events outside of classwork, the quiz will not be on Tuesday. I will move it to like Wednesday. And then the homework that was going to make due earlier in the week, I'll make it due either Wednesday or maybe Thursday. So that way students have, well, some time to do work, but they can hopefully space out and relax for a bit over the weekend. So that's the first two announcement about the quiz. Obviously, Monday is a holiday, so Monday quiz I was originally planning to have it on Tuesday, but I gave it some thought and I decided to have it on Wednesday. Okay, let's wrap up MOSFETs, a couple of examples, and then get into logic gates, logic circuits. Okay. Not synced yet. Okay. Should point after. Oh, there it is. There it is there. All right. Okay, so there were 2 or 3 examples I just wanted to go through, trying to determine the operating point of a MOSFET. Similar to how we did for BJTs, we can use graphical analysis or we can do an analytical analysis calculations, right? Graphical is rather straightforward. Load line analysis, which we've already seen for diodes, Zener diodes, BJTs, same approach. We have a MOSFET circuit here. And the MOSFET circuit is biased with VDD on the right and VGG on the left on the input side. But unlike a BJT, MOSFET does not have any input current, meaning the gate is isolated from the rest of the device because of the oxide layer. And so there is no current actually going into the device, which makes analysis a bit easier. Okay, so the givens are VDD is 10 volts, VGG applied on the input side is 2.4, RD drain resistance is 100 ohms. We're asked to determine the operating point, the quiescent point or the Q point values of the drain current and the drain source voltage. So IDQ and VDSQ. All right, so 2 unknowns similar to BJTs and diodes. We had diode voltage, diode current, ID and VD. BJTs, we had VCE and a VB, IB on the input side and VCE, IC on the output side. So here we only have to worry about the output side. A set of curves is already given to us right here, which is drain current ID as a function of the drain source voltage VDS. Right here, VDS. Okay. And let's take that out. Okay, so if you apply KVL on the output side, we have 4 voltage sources, 4 voltages, three, VDD, IDRD, and VDS. They should sum up to 0. So that's what we have here. Okay. Plug in the values for RD. And we obtain VDS minus 100 times ID is equal to 0. 2 unknowns, 1 voltage, 1 current. Load line graphical analysis. We want to plot a line. Line will have coordinates. We can take the 2 endpoints of the line, meaning the intersection points on the X and the Y axis. One here and one down here, right? Because that is the load line. So X axis equal to 0 and Y axis equal to 0 gives us the other 2 points. So we first plug in VDS equal to 0, obtain value for ID. Then set ID is equal to 0 and obtain the value for VDS. Those 2 points correspond here. Okay. Standard procedure. Apply KVL, input and output side. In this case, we don't have to worry about input because there's no input current going in. All we need to look at is VGS. VGS is not a concern for this particular problem because it only asks us to determine Q point values for ID and VDS. For that, we don't need VGS. Obtain the equation, plug in X equal to 0, Y equals to 0, and determine these 2 values. Once you have those 2 values, you plot the load line. And we are asked to determine for a value of 2.4 volts. And so VGG, which has a value of 2.4 volts, has a line right here. Now, there is no source resistance. Okay, so VGS is equal to VG, which is measured with respect to ground. And so if VGG is 2.4 volts, VGS is also 2.4 volts. We simply pick this line right here, this intersection point is our Q point. Again, same standard procedure. And we extend the coordinates of this point, gives us the Q point values for VDS and ID. So VDSQ is approximately equal to 4.75 volts, and IDQ is equal to 52 milliamps. All right, questions? Okay. Steps, okay? Right? All right, now let's look at same circuit, same characteristics, but it's asking us to find IDQ and VDSQ. We can, of course, use the graphical analysis, but let's look at calculations and equations. Now, this time we are provided with a threshold voltage of 1.4 and a K parameter value of 48.5 milliamps per volt square. Okay, VTN and K are provided. You're asked to find ID and VD. So let's say you didn't have the characteristics available, right? So there's no other way except analytical calculations. So first thing, is VGS larger than the threshold voltage? The answer is yes. Threshold voltage is given as 1.4 volts. VGG is 2.4, hence VGS is also 2.4. 2.4 is greater than the threshold voltage of 1.4. So MOSFET is on, it's not in cutoff. And when it's on, we have 2 choices, whether it's in saturation or active region, or whether it's in linear or the triode region, right? There's only 2 options once it's on, similar to a BJT. So we can assume linear or triode model and work, use the equations for the triode region, but let's assume saturation or active, right? We're trying to use this as a amplifier similar to a BJT. Then it makes sense to assume active mode for a BJT and saturation active mode for an FET or a MOSFET. So if we assume saturation, we can directly write out or directly calculate the value for IDQ, because we have the standard equation in the saturation region. It's K times VGS minus VTN square. We have all values available. We have VGS, we have K, and we have the threshold voltage. And I like this problem because the values just simply round up. VGS is 2.4, VTN is 1.4. And so the difference of VGS and VTN is simply 1. So 1 times K is 48.5. And so we obtain IDQ as 48.5 milliamps. Okay, 48.5 milliamps. Once we have IDQ, we can follow the same process. Apply KVL at the output side. We obtain VDD minus VDS minus IDRD equals 0. Plug in the values for ID and calculate VDS, which in this case is 5.15 volts. Again, as far as circuits go, this one is rather straightforward, minimal. There's only one component, drain resistance. There is a resistance at the gate, but there is no resistance at the gate, but even if there was a resistance, it wouldn't matter because we don't have any current going into the device. All right, so once we have both those values, we need to verify whether our assumption is correct or valid, right? We assumed saturation mode at the beginning of our analysis. So at the end of our analysis, we need to verify whether our assumption is correct or not. So to do that, we check whether VGD is greater than or less than the threshold voltage. So the VGD in this case would be 2.4 minus 5.15 gives us a negative value minus 2.75, which is less than the threshold voltage. So if it's less than the threshold voltage, then the device is in saturation or active mode. If it was larger than the threshold voltage, channel would be cut off. It's cut off, then it's in the linear triode. Sorry, it would not be in cutoff. And so it would be the linear or the triode region. Current would be increasing linearly with increasing voltage. Right? So this is where the channel is pinched off. So first approach was graphical. Second approach is using the equations. You can use either approach depending on what is given to us. Okay. So in both cases, the circuit is the same. Circuit is still the same. The values are exactly the same. But depending on what is available to us as an engineer, we decide which approach we want to take. Let's take a short pause. Let me know if you have any questions. Steps make sense? Any question about the steps? Okay. All right, let's move on to the next one. Okay, voltage divider bias or the self-biased circuit, or the third term is the 4 resistor bias circuit, right? Self-bias, voltage divider bias, 4 resistor bias, all the same names. Okay, 4 resistor bias. So we have R1 and R2, 2 resistors on the input side. Output side, we have a drain resistor and a source resistor. All of them are connected to a 30-volt VDD supply. 30-volt VDD supply. And We are given the threshold voltage, we are given the value of K, and VDSQ is also given to us. There's a reason for VDSQ. Otherwise, we would never be able to solve the problem. Okay, so VDSQ is given to us. What else? We need to determine VGSQ, meaning the value of VGS at the Q point, drain current IDQ, and source resistor value RS. Okay, so this could be similar, could be described as a design problem, meaning we want our device to operate at a VDS value of 8 volts, and we need to determine the value of the components, meaning the source and the drain resistor. To make our job easier in this example, the drain resistance is given to us, so we can determine then what the ID current is. Okay. All right, so first things first, if you have a voltage divider network, we saw this in the BJT earlier, we need to reduce these two resistors down to its Thevenin equivalent network. Thevenin equivalent network is right here because these are the terminals that are going into the FET or the MOSFET, right? These are the two terminals. So this would become VGG, and then R1 and R2 will combine to give us RG, the gate resistor RG. Okay, and that is done applying voltage division and resistors in parallel. For convenience sake, both resistors R1 and R2 are the same value, 1.2 mega ohms. Doesn't really matter what value it is. If you have two resistors with the same value, voltage is going to get divided in half, right? Split equally across both resistors. You could apply 30 volts to like two 10 ohm resistors. Each resistor will have half of that, which is 15 volts. So 1.2 mega ohms in parallel with 1.2 mega ohms gives us a total equivalent resistance RG of 600 kilo ohms. So that's what we have here, 600 kilo ohms. VGG again, simply be divided in half. So it's 15 volts across both resistors. The 15 volts is going into the gate terminal. Okay. The Thevenin equivalent circuit. Any questions? Anything I can clarify? Good. How at this? IG, but IG would be equal to 0. Yeah. It shows IG, but theoretical analysis, IG would, for all intents and purposes, equal to 0. All right, so we apply KVL at the input. We obtain minus VGG plus IGRG plus VGS plus ID times RS equal to 0. However, as we just noted a few seconds earlier, IG goes to 0, right? IG goes to 0. VGG is 15 volts. And so the circuit can be reduced to VGS plus IDRS is equal to 15. Okay. So VGS plus IDRS is equal to 15. Now, we have two unknowns. ID is an unknown. VGS is also an unknown. All right. So we keep that on the side for now. And we apply KVL at the output side. On the output side, we have 4 voltage drops. We have VDD, we have the IDRD, we have IDRS, and we have VDS. The 4 voltage drops on the output side. So VDD minus IDRD minus IDRS minus VDS should be equal to 0. There's a subscript of Q attached to ID and VDS because you're trying to find the Q point values for both ID and VDS. Now, if we do this, we end up with actually 3 unknowns because VGS is an unknown, ID is an unknown, and VDS would also be an unknown. But again, the parameters of the problem specify VDS is given to us. We want to design the circuit with a VDS fixed at 8 volts, okay, which is given earlier problem. Okay, so when we try to solve this, if you have 2 unknowns in a circuit, if you have 2 unknowns, more likely than not, we may end up with a quadratic equation. So what we are going to do is, since ID is unknown right here, we are going to obtain an equation for IDQ. Okay, we're going to manipulate and obtain an equation for IDQ. To obtain the equation, we plug in this into the other equation. And we can obtain VDD minus IDRD minus VDS minus 15 plus VGS. So, and then we obtain this. Okay. We have this equation from the first KVL. We express the equation in terms of ID. Remember, ID is something we want to determine. So we always want to write equations for the quantity that we wish to determine. So ID times RS is 15 minus VGS. We take that and we plug it into the second equation. So you plug it in the second equation and rearrange the terms. We obtain this expression. ID is to be determined, so we rearrange everything with ID on one side equals everything else on the right-hand side. And so we obtain this. IDQ is 1 over RD times VDD minus VGG, VDD minus VGG minus VDSQ plus VGS. Reduce that a bit further, and you obtain 15 minus VDSQ plus VGS divided by RD. Okay. This is simply the voltage drop across the drain resistor. IDRD is the voltage drop across the drain resistor. So that's equal to 15 minus VDSQ plus VGS. Okay. Now, the assumption is that it's still in saturation, okay, saturation active mode. So from the equation for ID in the active saturation mode is IDQ equals K times VGS minus VT the whole square. We plug or we equate them together, we rearrange the terms, and we obtain our quadratic equation in this form, where then the only unknown left is VGS. Okay, the only unknown left is VGS. Now, this is a solved example, right? So if it's a solved example, we do not have to determine as an engineer. Now, but as an engineer, if you're looking at a circuit, you might try multiple pathways, multiple equations, trying to figure out what that single equation might look like. Okay, so this is just showing you one of the potential pathways, right? As an engineer, you might have multiple quantities available to you, and then you can pick and decide which equations you'd like to use. Right? In this case, with the example that we have on hand, we are provided with certain values. So this is the best pathway, and this is obviously solved for us. So we obtain a quadratic equation. The coefficients are all containing quantities that are known to us. So we have threshold voltage, we have K, we have RD, we have VDS. Sorry, not VDS. Yeah, we have VDS, we have VDD, and we have VGG. So all of those are available to us. We plug in the values, and we obtain these two. And once we obtain those two, solve for VGS, we obtain two values. The roots of the equation are 6.48 and 1.97. So if you have these two values, how would you decide? Answer is already there. It can't be less than 4 volts. If it's less than 4 volts, then our device isn't cut off. So VGS value must be larger than 4 volts, which the first root is, the second one is not, right? Now, if both of them are less, then we made an error somewhere in a calculation. If both of them are higher than 4 volts, well, that's a real life scenario you would face as an engineer. Okay, so then you'd have to pick and decide which one would fit your application the best. And again, this is a solved example, so the values are chosen in such a way that only one value would make sense and only one value would work. And so 6.48 works, so VGS value is 6.48. We take that value and we plug it into these above equations. Once we do that, we can obtain ID value as 1.35 milliamps. And once we find that, we can plug it into the KVL equation that you obtain at the second step, and we can find RS as 6.32 kilo ohms. Okay. Now, if this, let's say this was a real life example and it didn't work, then we would kind of like start off with this value for RS, change it, either increase it or decrease it a bit. And so then ID would change, and then ID changes. Then you can work backwards to see what would fit, what value of VGS would be required to obtain that specific value for ID. Okay. So again, a design problem in real life as an engineer, you'd have multiple variables. There'll be multiple unknowns. So you'd have to pick a starting point, meaning you assume the state of your device, you assume the state of your system, and you choose some values for some of the components from your calculations, and then see whether your system works. If it doesn't, you go through multiple iterations, which is what an engineer is supposed to do. All right, let's take a pause. Let me know if you have any questions. I'll go back to the top. So why VGS should be larger than the threshold? If VGS is less than the threshold, then the device is cut off. That's not on at all. The previous one, I believe you're referring to this. That's VGD, not VGS. So if our threshold, if my right hand is the threshold, the gate voltage, the gate to source voltage, VGS, must be larger than the threshold. Otherwise, the channel would never form. If it's less than the threshold, no channel. Device is cut off completely. Now it must be larger than threshold. So it's larger or greater than threshold, channel is formed, it's operating. But now we have two options. Once the device is on, it could be in the linear region, which is to the left side of the curve, where the current and voltage have a linear relationship, or it could saturate and become a flat line. If it's in the linear region, VGD would also be greater than the threshold voltage. Because the channel is now larger, there is more space for the electrons to flow through. Okay, so VGD must be greater than the threshold voltage. If it falls below the threshold voltage, not VGS, but VGD falls below the threshold voltage, the depletion region at the drain end will expand. And when that expands, the channel begins to shrink. And so then it goes into pinch off, current just becomes saturated at a particular level. And so that's VGD, not VGS. Any other questions? Okay. All right. So the next example is exactly the same. These are examples in the book, by the way. So corresponding to the notes and the talk that we do in class, the explanation we do in class, you can also look up the solved problem in the book. Oftentimes solved examples in books, they skip through a few steps. And so it's left up to the reader to understand what it is. But hopefully students can, from the talk, in-class talk and the laid out example, should be able to understand the process. So the second one is again same from the book. So what I want students to do is use it as practice without looking at the book first. I mean, without looking at the solution first. Okay. So the parameters are there in the book. Solve through the exact same steps. Do not look at the solution. Just compare it once you are done. Okay. And then if you run into any issues, just let me know. Just reach out to me. I'll be available over the weekend. Okay. So I'll be available over the weekend. All right. From here, let's turn our attention to applications. So, should be above. Logic gates, CMOS technology. What is CMOS? Complementary MOS. Went over this, maybe class, maybe I definitely went over this in the lab. We have N-channel MOSFETs, P-channel MOSFETs. Both are complements of each other. And so if you have circuits with both N and P-channel MOSFETs together in a circuit, forming one component, that's known as complementary MOS and CMOS, which CMOS has been used. You might have come across this in your first year, probably even before college, perhaps. Right? That's where the name comes from. So logic inverters using NMOS and pull-up resistors. So we learned about pull-up and pull-down resistors in the lab. This is a bit more theoretical explanations. I'm assuming y'all are familiar with all the gates, right? The AND gate, the OR gate, and so the NOT gate is basically inverter gate, A not Z, or in other terms also A bar. Are you all familiar with the bar symbol, right? Okay. All right, so A and A bar. So output Z is A naught. We looked at the end of the BJT chapter. Remember, we showed a single BJT inverter circuit. The BJT is on or off, depending on its states. The output could be inverted, right? Even in an amplifier, we know that if you apply a sinusoidal or any kind of AC waveform, the output is inverted, right? So that bar represents inversion or the opposite of output. But in digital logic circuits, when we talked about logic 0 and logic 1, we're talking about 0 volts and 5 volts, right? So 0 volts and 5 volts. So if A is 1, meaning the input A is 1 or plus 5 volts, the output is 0 or 0 volts. If the input is 0, output is 1 or plus 5 volts. Implementation using a single N-channel transistor looks like this. The transistor has two modes of operation, right? We can use it as use it as an amplifier similar to BJTs, or we can combine the two modes of operation, cutoff and linear region, to say it's either on or it's off. If it's cut off, then the device is off. If it's in the triode region, we say it's on. Okay. And so if we have this transistor, and it's cut off or it's on, we can combine it to use it as a switch. Now, when we use it as a switch, if it's on, it's going to connect the output Z directly to ground. Because once it's on, the only resistance that is path of the output is the channel resistance. Okay. Because current is flowing through the channel, and the channel current is limited. It's not infinite. The channel current is not infinite. We can model that flow of current using Ohm's law, and we can say the channel has some resistance. And so the resistance is, of course, very small. That's where it comes from. So because it's very small, the voltage drop across that model resistor is very small. And so the output is approximately close to 0 volts. Very close to 0 volts. And so when it's on, we get logic 0. When it's off, we get logic high. That's an inverter circuit. So it's 2 o'clock. If you have to leave, you can leave. I'll continue on for a few more minutes. And so that's how it works as an inverter. You can use it. You can use a single transistor and create a simple inverter circuit by simply applying a pull-up resistor. Okay. And of course, this is rather straightforward to do. You can do this in the lab. You have your MOSFET chip, hook it up, apply plus 5 volts at the input, at the gate, and you would obtain 0 at the output. If you apply 0 at the output, meaning at the gate, you obtain plus 5 volts at the output. Now, you can create other kinds of other kinds of gates using these MOSFETs. OR and NOR circuits are basically logic OR is mathematical summation, right? So A, B, and output Z is equal to A plus B. 0 plus 0 should give us 0. 0 plus 1 should give us 1. 1 plus 0 should be 1. And 1 should also give us 1. So if any of the inputs are high, the output is also high. That's what it means. And we can do that by combining 2 transistors and connecting them in sort of parallel. So we have A and B, which are going as inputs to the gate. That's our input to the gate. The drains of both transistors are connected together. And the output here would be inverted. Okay. So by default, we obtain a NOR output, right? A NOR output. So let me just write it as Z bar. A plus B bar. Because if you have 2 in parallel, again, you can model this as a pull-up resistor right here. When they're on, resistance is small, gets connected to ground. Output is 0, right? If any of the transistors is on, there's a direct pathway to ground. So a quick summary. OR gate is what? 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1 should also be 1. NOR gate is the complete opposite. If even a single input is 0, then the output is also 0. So in a NOR gate, This turns out 0, 0, 0, and 1. So if you look at those two transistors, if any single one of those transistors is on, you have a direct pathway to ground. Meaning if either A or B, if A or B is 0, output goes to ground. And so okay, so if either A or B are 0, then the output goes to high, not low. And that's why we get a inverted output. Hence, we get a NOR gate. And if we wish to have an OR gate, we have to add another inverter at the output. Separate inverter to obtain an OR gate. This is typically true for BJT and FET circuits. We would obtain a inverted output. Like if we wish to obtain an AND gate, we'd create a NAND gate first, and then we connect a inverter at the output. Okay. Because by default, the configuration is such that when you connect MOSFETs in series or parallel or complementary to each other, the output would be inverted. So the first two transistors give us a NOR gate, and then we have to add a separate transistor inverter at the output to obtain an OR gate. All right, logic AND A dot B, which is not quite multiplication, but very similar to mathematical or arithmetic multiplication. AND gates, you're simply cascading them together. So you have two switches in series. You have the two gates acting as the input. Right? Two gates of the transistors acting as gates of the AND gate. And so when this time the transistors, both transistors must be on in order for the output to change. Okay. So if if they are on, you have a pathway to ground. The inverter, sorry, not inverter, the output at this point is again Z bar. We obtain a NAND gate. Both of the transistors must be on in order to provide a pathway to ground. So A and B must both be 1. Transistors turn on, connects to ground, output goes to 0. So 1 and 1 gives us 0. For all other combinations, 0 and 1, 1 and 0, or 0 and 0, either one or both the transistors are off. Transistors are off, then the output is VDD. So NAND gate. Quick truth table. NAND gate output. You'll remember NAND gate. 0, 0 is 1. 0, 1 is 1. 1, 0 is 1. And only 1 and 1 is equal to 0. So if A and B are both 1, transistors are on, it connects to ground. Output by default is 0. And so two transistors give us a NOR gate, or it would give us a NAND gate. If we wish to have an AND gate or an OR gate, we need to connect a separate inverter at the output. Okay, you connect it in series, you get a NAND gate. You connect it in parallel, you get a NOR gate. And the more transistors you connect, the more inputs you can create for your AND gate. You can have like a 5 input or a 10 input AND or NAND gate. Just connect everything in series or connect everything in parallel, and you can do so. Okay. All right. So I think we'll end class here today, and we'll pick up here again on Tuesday. I will be available over the weekend. So if you have any questions, you want to reach out, feel free to do so. Yes. So the benefits of using MOSFETs or BJTs, yes. One of the biggest ones is does not require any input current. And because it has very high input resistance or input impedance, does not require any current to flow into the circuit. And so that's one big advantage. And over the years now, MOSFET processing or creation has taken over. So lots of tons of research has gone into developing CMOS technologies, and so it's very, very cost effective to build circuits with MOSFETs versus BJTs. So less power hungry. That's the biggest advantage. Any other questions? Okay, we're in class here today, and we'll pick up here again on Tuesday. Quiz will be on Wednesday, not on Tuesday. Also, lab class is not anyway. I'll post an announcement separately for the lab class, so don't worry about that.